Did you know that Git CLI and GitHub CLI, they both use macOS Keychain to store credentials such as GitHub tokens, which is a very secure and robust way of protecting those credentials. But did you know that the way these credentials are stored in the macOS Keychain by these tools allows every process to access those credentials via shell in plain text?
Jesus Christ.
My name is Martin, and today we will talk on how can we protect API credentials when we are using AI agents. Potentially multiple AI agents on the same machine, and with each of them having different set of credentials. Specifically, let's talk about two common CLIs that we in our AI coding agents use: Git CLI and GitHub CLI. We use Git CLI in order to make a commit and in order to push that commit to a remote branch on the GitHub server, in our case. And we use GitHub CLI in order to create a pull request, in order to review a pull request, in order to merge a pull request, and in order to also create a repository in the first place if that repository does not exist. So how would we allow our AI coding agents to use these CLIs in a secure way? Well, we would create a GitHub token with fine-grained permissions, and each of the agents would use its dedicated token to make a request, a remote request, using either Git CLI or GitHub CLI. So how can we make sure that an AI coding agent could use these CLIs with a dedicated GitHub token, but without exposing that token to the AI coding agents, especially in a case when we're using OpenClaw and it has full access to the file system, it has full access to the shell commands? Well, the idea is simple, is to use a built-in macOS keychain. The idea behind macOS Keychain is simple. It lists passwords, and for each password there's an entry which is called access control list, or short ACL. And this entry defines application which can access that particular entry without user prompt. Because a user prompt in case of autonomous AI agents would be super annoying, like on every Git push, on every pull request creation. We don't want to have that. But we also want to protect our credentials, and the keychain design protects us. We have different types of the keychain on the macOS. On the one hand, we have a file-based keychain, and it consists of the system keychain, which stores all system data, for example, such as Wi-Fi passwords. And we also have a login keychain. In fact, each user on the macOS gets its own login keychain protected by that user's password. And for example, our standard user where OpenClaw agent is running is using the login keychain of that standard user. And we also have the data protection keychain, which is a newer type of the keychain. And depending whether we are using iCloud synchronization or not, we could see the items such as local items when we are not using iCloud synchronization. Otherwise, we would see iCloud items. In our episode, we will focus on the file-based keychain, specifically on the login keychain. So also when we talk about the multi-agent identities, because they are belonging to the same standard user, they're all sharing the same login keychain. And it's also something that Git CLI is using and GitHub CLI is using, as well as some other CLIs. And we can also use the built-in keychain access app to check the items stored in the login keychain. For example, we can check the GitHub token stored, and we can also see which apps are in the allowed list for each GitHub token. And this is how I found out that the GitHub token stored by the GitHub CLI has the security command shell listed in the access control list, meaning it's basically up for grabs from the shell as plain text. We have here In my case, Toby, OpenClaw AI agent, and it wants to create a pull request. So it uses the GitHub CLI, and the GitHub CLI goes to the keychain, and in the keychain, it tries to access the token, and the macOS compares the entry GitHub CLI against the application GitHub CLI using the code signature check. And because the token was created in the first place during the onboarding, when we have executed GitHub CLI login, the application is in the allowed list and the token is returned, and the pull request is created on the github.com. Now let's imagine that the Toby, because it has access to all the shell commands, it has access to all the file system within its workspace, wants to access token itself. So for example, it could use a terminal application, it could use some other commands, but because only the GitHub CLI is listed, so if Toby tries to access the keychain, then the request would be denied because neither Toby nor the terminal app nor other app are listed in the ACL. Now let's talk about how GitHub CLI stores the password exactly in the keychain. So actually it uses a helper, and in fact it uses a helper which is a security command, and security shell command is used is a built-in command in the macOS to access the keychain item. And then we see that the GitHub CLI does not call the keychain directly, but instead it uses the security, and that means the last application accessing the keychain would be in the allowed list for the GitHub token, not the GitHub CLI. And this means that anyone could execute this because the security is now in the allowed list, and meaning everyone could execute the security from the shell to print out the token as plain text to the shell. So how can we fix this design? Well, we need to remove the last process in the chain, in this case the security, because the security allows anyone to retrieve the credentials as plain text. So we'll need to remove this. And because the GitHub CLI is not able to call the keychain itself, neither we want to rewrite the GitHub CLI from scratch to integrate this functionality within the GitHub CLI. The idea is to use a GitHub wrapper. So we will introduce the new application, a very thin application, GitHub wrapper, and the GitHub wrapper will access the keychain when we call it. And because we will also onboard the credential using the GitHub wrapper, it will already contain the GitHub wrapper in the ACL. So we will use the GitHub wrapper to onboard the credential into the keychain. So the GitHub wrapper calls that credential, the keychain returns the credential, and then the GitHub wrapper calls directly the GitHub CLI. That means there is no credential leak because the GitHub wrapper does not return credentials as plain text into the shell. Additionally, we would also add support for the multi-agent profile into our wrapper, which is by default not available by the GitHub CLI, or it is not very straightforward to switch the profiles, because in some cases you may want to have multiple agent identities on the same machine as part, for example, of the same OpenClaw instance, meaning they're still sharing the same user as of the macOS, but we need to have the means of switching their credentials. And we will implement it by using the flag --s. So for example, we can say GitHub wrapper --s, for example, Toby, and then we specify the command that we want to pass over to the GitHub CLI, for example, PR to create a pull request, and in the keychain we will also have different entries for each agent profile. But it still have one weak point, specifically the GitHub CLI. So GitHub wrapper, when we call the GitHub wrapper, it fetches the credentials, fetches the GitHub token, and passes the credentials via the environment variable to the GitHub CLI. But what if someone were to replace this executable with a malicious one and thus extract the credential, extract the GitHub token. So basically the solution is that we need to verify this executable because before verifying it. So before calling the GitHub CLI, we would check if the signature of that executable is valid. We would also not use potentially the path variable, but we would potentially hard code the system path where GitHub CLI is installed. So that means no one could just overwrite the path environment variable and make GitHub wrapper execute the executable from a different path. And also ideally, we would also want this to be installed with the sudo command so that the agent is running at a standard macOS user would have no rights to replace that executable. So this way, we're effectively ensuring the supply chain and the provenance. So we are verifying the signature of the executable in the first place, and we invoke the signature from the system path where we know that the agent which is running as a standard macOS user is not able to modify that executable. Now let's talk about Git CLI, because we need both Git CLI and GitHub CLI configured for our AI coding agents to make contributions to the github.com. So we need both CLIs, and they use different procedures regarding how they store tokens in the keychain. So for example, here, Toby, my AI coding agents, would like to push a commit to a remote branch. It executes the Git CLI. Git CLI goes to the keychain, and the keychain checks if the Git CLI is allowed to access the token, but because the token was created during the onboarding, the keychain returns the token, and the request goes through to the github.com. However, if we go to the Keychain Access app on our macOS, we see that it's not the Git CLI which is in the allowed list here, but it's a helper. It is a bit more complicated in case of the GitHub CLI, but still with that helper, you can very easily from the shell to get, you can get very easily the stored GitHub token as plain text without the user prompts, because it's not the Git CLI which is in the allowed list, but the Git helper. Now with the Git CLI, in order to protect credentials stored in the keychain, we need to come up with a more complicated solution. So we have here Git wrapper, which is our entry point. We will use the Git wrap instead of the Git CLI, and the Git wrapper will call the Git CLI, and the Git CLI will call the github.com. So it's the same process we had with the GitHub CLI. And the Git wrapper will call the keychain, and because the credentials informations were onboarded during the initial call to the GitHub wrapper will be in the allow list for that for the credentials. In addition to the token, it will also contain the username and email, because we also need username and the email when we are invoking git commit command. So we need to pass those as well. And because we want to support multiple agent identity as part of the same OpenClaw instance within the same login keychain, it's very handy to have those stored in the keychain. And then when Git wrapper calls the Git CLI, we pass those via environment variables, meaning we don't need to invoke git config command before invoking the Git wrapper in order to make a commit with a specific agent identity. Now the tricky part is how to pass the GitHub token, because we cannot pass the GitHub token via environment variables. It doesn't work. But we can pass the program which will override the built-in credential helper. So by default, when we don't pass anything, the Git will invoke the built-in credential helper, which we have seen previously in the key access app, that it was in the allow list for the GitHub token. But now we don't want to use that credential helper. We will use our own credentials helper. So there will be a second app that we will design. So this will be called Git Ask Pass. and we will pass the path. We will pass the path to this app in the environment variables. That means the Git CLI will call our custom credentials helper. How our custom credentials helper will get these credentials in the first place? Because as you see, it's not in the allow list in the keychain item. And the idea is that we will actually set up a Unix domain socket. So there will be a channel connection between our git ask pass custom credential helper and the git wrapper. Or more specifically, we will have a dedicated component, part of the git wrapper component, which is called broker, and basically it will maintain the socket channel. That means when the git CLI invoke our custom credentials helper will fetch the credentials from the broker without accessing the keychain, and then it will pass the credentials back to the Git CLI, and the Git CLI will invoke remote actions against github.com. And additionally, when GitHub wrapper will call Git CLI, it will obviously pass the socket path so that our custom credentials helper will know which socket to listen to, because basically Git CLI will pass all the environment variable that we provide here, so they all go here. So the Git CLI will forward them, which is very handy. And additionally, we will also generate nonce, a random number, so that which we will also pass here from Git wrapper to the Git CLI, so that when our custom credentials helper will try to get the credentials from the keychain, it will provide the nonce, and only if there is a match, the credentials will be provided. Because we need to account for a case that socket could be misused by another application, because each socket has a path, and in theory it is possible for some process running under the same user to find about the socket path and misuse it for its purposes, and that's why we are using additionally the nonce. So only if there is a match, the credentials are provided. So this design is a bit more complicated, but because of the use of the socket channel, but this is the only way we can actually make credentials work in a secure way. And also additionally, we will also provide the same as with the GitHub CLI. Also, Git wrapper will provide the way to dynamically switch agent identities. So for example, you would say git wrapper --s, for example, Toby, the identity, so it will fetch all the details from the keychain. So they actually stored as a JSON blob. So it will have like 3 fields: token, email, and name. And then it will pass it into the git command. So we can say git wrapper --s Toby, and for example, commit with a specific message. And of course, we want to also protect against attacks on the supply chain and to ensure the provenance. So for this, in a similar way as we did with the GitHub CLI, when Git wrapper would be calling Git CLI, it would be calling it only from the system path. In this case, it's user/git/bin. It will ensure that the certificate is signed by Apple. And this path is also guarantees that in case our AI agent is running as a standard user, which should always be the case, that means the standard user is not able to manipulate this folder, nor it will be able to manipulate this executable. That's why we can be sure that this is the exact Git executable that we are running. And also, before passing the path to the Git ask pass to our custom credentials helper, it will also verify its hash, because it could be potentially a plausible attack that someone would replace this custom credentials helper. And we will also install this, for example, in this user local bin using the sudo command of an administrator. This makes sure again that it is enough for our Git wrapper to just check the hash, check that the hash matches, whatever hash is baked into the Git wrapper, and basically it's generated during the build process. During the build process, we build Git wrapper, we build Git ask pass. then we calculate what is the actual hash of the git ask pass, and this will pass to the Git wrapper, and it's rebuilt with that hash. So it's hard code. You can check both GitHub CLI wrapper and the Git wrapper in the GitHub repository using the link in the description. My initial video for this video was actually not the security aspect. It was about extending the GitHub CLI, or not really extended, but configuring the CLIs for my case, which is a multi-agent setup under the same user, but this turned out to be a lesson in security. So I'm really looking forward. What do you think? Please leave your comments below, and please share if you have any similar stories with security, potentially with the supply chain attacks. I'm looking forward to hearing your comments. Thank you.